All right, welcome back, everyone. Welcome back to the oxygen session. We hope that after your lunch, you'll all be bubbling up with questions for our speakers. Come on. Yeah, okay. All right, so we have two more talks to continue on, and then we'll have a panel discussion. So be ready for that. And Jeremy Testa is up next. We're going to continue on with coastal oxygen. Take it away.
Thank you. Can everybody hear me okay? It's on. Yeah. How's that? Any better? Glad I asked. Okay. Thank you for having me here in this session, and it's my first time at OCB, so it's both fun and exciting to be here. And as the title of my talk suggests, at least broadly, I'm going to talk about BGC chemical controls on oxygen depletion across different systems, really. And so by taking this cross-system approach, we're sort of forced to address different timescales. And I just want to acknowledge my co-conspirators. Katja Fennel is my co-author on the main paper that I'll be talking about today, but my colleagues at UMCES, Laura Harris and Walter Boynton, have also been instrumental in this work overall. So Katja and I were tasked with doing a paper that sort of reviewed the biogeochemical controls on hypoxia, and we took this perspective that we wanted to do something cross-system, but we didn't want to sort of do this qualitative, broad written comparison. So we wanted to try to do something where we could use data to do sort of a uniform quantitative comparison, even if it was simple, to put all of these different diverse coastal and estuarine ecosystems in the same space. So the approach I'm going to talk about today is to perform this synthesis of just what's available in the literature of oxygen consumption rates in both the water column and the sediment, and how those relate to water residence time. And so the concept here is that the degree of oxygen depletion, which depends on the magnitude of the biogeochemical oxygen consumption rate, is sort of balanced by the physical replenishment rate, which we'll sort of characterize with residence time, because that's the kind of simple data we have available. So I just want to point out that in doing so, I'm going to highlight the diversity of timescales in which oxygen is depleted in coastal environments, and consider that oxygen consumption is really driven by a variety of sources in the nearshore estuarine zone, wetlands, the watershed, and nutrient-fueled autochthonous organic material. So many of you may be familiar with these types of systems, but I just wanted to highlight sort of the full diversity of the type of aquatic systems and the types of timescales of oxygen depletion that they have. So this is an example from the Corsica River estuary, which is like a 1 meter shallow estuary in the Chesapeake Bay region. It's really highly nutrient enriched, and you can see this oxygen time series over a year. And what these lines represent is a day's or hourly oxygen data. So you can see that it's varying from supersaturation to what we would call hypoxic over the course of 24 hours. You might contrast that with the Pamlico River estuary in North Carolina. This is data over the years, but you can see that there's just sort of episodic hypoxic events that happen in this system. And you can also compare it to a place like Chesapeake Bay, where there's seasonal hypoxia, and so oxygen, as Malcolm showed earlier, comes down to low levels, stays that way for 2 or 3 months, maybe 4, finds its way back up with overturn and temperature increases in the spring, or in the fall. Okay, so what we did is we chose systems that had data for water column respiration and sediment oxygen uptake rates and had some estimate of residence time in them. And we were mostly focused on nearshore and coastal systems. So the systems that we primarily considered in the analysis are represented here, and I'll talk about a little of them in detail. But the perspective that we took really emphasize this idea that despite the different sizes, the different depths, the different freshwater inputs, the different circulation regimes, that there's basic processes happening in all these systems that we can sort of quantify at least in a mean state. And so as we've seen and as everybody in this room knows, there's air-sea exchange, there's sediment uptake, which tends to be important in these shallow nearshore zones. There's a balance between primary production and respiration, and of course there's many different modes of physical transport, both in 1, 2, and 3 dimensions. So just to highlight some of the systems we focused on here, we considered at least one upwelling shelf, which is off the coast of Namibia, but the Oregon coast we sort of wanted to look at but didn't get the data for. But these are systems, as we've seen, Sam showed earlier, that have open boundaries. They may have big rivers, they may not, and that low oxygen tends to be naturally driven in these places. Then we have river-dominated shelves, the Gulf of Mexico, the northwestern shelf of the Black Sea, the East China Sea, and the Pearl River estuary. These are broad shelves that tend to have major rivers, and oxygen depletion is driven by a combination of physical forcing driven by climate and also anthropogenic sources. And then we have what we call retentive systems, which include Chesapeake Bay, Long Island Sound, the Gulf of St. Lawrence, and the Baltic Sea. Places that maybe in a comparative sense have relatively moderate inputs, but they have restricted circulation. It tends to trap nutrients and organic material, and so therefore there's sort of an inherent vulnerability to hypoxia. So if you just look at the maximum hypoxic area that's reported in the literature for these places and related to nitrogen load, you can see, or you could try to believe, that there's a positive relationship there, and this really reflects both the nutrient-full phytoplankton production and respiration that comes from this, but it also sort of indirectly related to the freshwater discharge that originates here. And just that where you have bigger loads, you tend to have bigger systems, so they tend to have bigger hypoxic areas. And so I just want to lay out this really simplified framework that we use to characterize and compare these systems, kind of in a mean sense for a control volume. So what we wanted to do is compute a time scale of hypoxia for each of these systems. And so we did this simply just by considering an initial oxygen concentration, ox-ini, which we fixed, and then the net oxygen consumption rate, which is the sum of the sediment oxygen uptake and the water column oxygen uptake in each of these systems. And so, hypothetically, you could see how over time, if you had a low initial oxygen concentration and low respiration, you might have a relatively short time to hypoxia. But if you have high initial oxygen concentration, you would need high respiration rates to get down in the same amount of time. And with high oxygen initial concentrations and low respiration, you have a relatively long time to hypoxia. So it's sort of a simple way to sort of consider how long it would take each of these systems to get to hypoxia, given the same general starting point. So the next thing we can do is, if we have an estimate of residence time, which we pulled from the literature, we can look at the ratio of these two things, both of which have the unit of day. So you get this non-dimensional number gamma that relates the time scale of hypoxia, how fast it takes to get to hypoxia, to the residence time. And so we hypothesized that this number gamma needs to be less than 1 for hypoxia to occur. Basically, you have enough respiration to drive to hypoxia conditions within the residence time of the system. Okay. So this is a table from our paper, and I just want to use it to highlight the 8 systems that we're able to obtain this kind of information for. And so you can see that most of the retentive systems we had are in here: Chesapeake Bay, Pearl River, the Baltic, Long Island Sound. And then we have some of the river shelves here: the Gulf of Mexico, the East China Sea, and the northwestern Black Sea. And the residence time estimates that we're able to pull out of the literature, you can see, are sort of varying by orders of magnitude, where you're something on the scale of days in the Pearl River, and you're on the scale of years when you come up to the Baltic Sea. So we also computed the hypoxia timescale. Remember how many days it takes to get to hypoxia given an initial concentration. And you can see that those numbers are varying by orders of magnitude as well. So it just sort of amplifies the fact that there's just a lot of variability in these timescales in these different systems. So we put these systems sort of on the same space to try to consider what a system's vulnerability to hypoxia might be. So on the x-axis here is residence time. On the y-axis is the hypoxia timescale. And this is the 1-to-1 line. So anything that's in this space is basically hypoxia vulnerable. It can drive to hypoxia within the time scale of the residence time. And that anything that's up here is is the opposite, right? Oops. Here we go. So if gamma here is above 1, it indicates that there's not enough local respiration to drive to hypoxia in this system. So it sort of suggests that there must be some low oxygen source water, and thus a lower initial oxygen concentration that puts these systems here. So the Gulf of St. Lawrence and then Mibium Shelf, at least the way we did this, fell into this space. And I think this is consistent with the literature. So I want to spend the last part of my time taking this sort of framework we developed and applying it to systems that are really small and have really rapid hypoxia timescales. So I'll come to some of my work in the Chesapeake Bay here and focus on 2 systems. The first is the Corsica River, which is a shallow system that's on the eastern shore of Maryland over here, and then Rock Creek, which is another small tidal system, which is just sort of within the tidal waters of Baltimore. Both of these are really enriched places. This one because there's a lot of urban nutrients, this one because there's a lot of agricultural nutrients. And so just to give you a sense of what these places are like, their depth for the Corsica River, it's about 1 meter on average, and Rock Creek is somewhere between 2 and 3 meters, so they're really shallow. If you sort of estimate a hypoxic area in kilometers squared, you can see that these are at 4 and 0.5, and these are 3 orders of magnitude smaller than most of the systems we compared in this bigger analysis. And the chlorophyll, kind of on average in the summer in these places, typically exceeds 100. So these are just incredibly productive, incredibly eutrophic places. And unlike the bigger systems that I showed, we actually have what you might call a directly observed hypoxia timescale, meaning that we have sensors there and we can sort of watch hypoxia develop there in a short time. So the other thing I wanted to point out about these places is just to put them in the space of nitrogen and phosphorus loading on a global scale. So this is a cross plot of phosphorus load for a given area versus nitrogen load for a given area. And this dashed line here is the Redfield ratio, and these are estuaries across the globe. And if you put the Corsica River and Rock Creek there, you can see that they're relatively high relative to systems around the globe. And that a lot of the places up here are sort of the estuaries near Tokyo, near Baltimore, near Boston. They're just some of the more eutrophic places that we have data for. Okay, so I want to start with Rock Creek. Here's this little tidal creek. Here's the Patapsco River. Baltimore is up here, and Chesapeake Bay is out here. And what's unique about this place is that in the 1980s, this place stunk of sulfide, and there happened to be a real strong motivation in the community to do something about it. So the local county actually paid to install an aeration system in the creek, and they installed the aeration system right up here in the most upper part of the system. If I could only use a mouse. I'm not a Mac user, by the way, so. Can I hit enter? Oh, there it is. Well, you get the idea. So the way they actually do this is they blow compressed air from land into this array of aerators. And they're actually not aerating the water. They're just basically mixing it and destratifying it. And so there's these boils sitting here, and you can see the array here. If you fly low over the system, you can see this array of aerators over the creek. And so this is a place where there's clearly a lot of natural tendency for hypoxia. And my colleagues did an experiment in 2012 where they worked with the county to actually turn this system off. So that we have the capacity to sort of experimentally deoxygenate or oxygenate a system and then deoxygenate it. And so what you can see here, a little less because it's bright, is that this is a period when it's aerated, this is when it's not aerated, this is the experiment, and this is when it's aerated again. And apologies, these units are going to be in milligrams per liter for the most part going out. I'm sort of stuck between two worlds, and so I'm always in that space. But so you can see here that the aerators, right before they are turned off, oxygen was at 10 or 11 milligrams per liter. Within 11 hours, it's pretty much gone, hypoxic and oxic. And this purple here represents basically everything below 1. And you can see over the course of 2 weeks that that low oxygen water is creeping from being at 3 meters up to near the surface. Overnight having some jaunts into the surface. And you can see that there's some diel cycling going on here, where you have these supersaturated oxygen concentrations. These aerators are also mixing the water, so the phytoplankton are sort of getting stuck in the low light conditions. You turn them off and boom, you have a bloom. And so now you have this really incredible gradient. So another thing that happens when you turn the aerators off is that there's sort of an expansion of this low oxygen water over space. So here's the aeration zone, and now this is horizontal space. And notice the scale here. This is about 1,500 meters. So the aerators are here, and this is on a day when the aerators were running. And then they were turned off the next day. And you can see that this low oxygen water has sort of now moved far beyond the footprint of this aeration zone. And that there was some low oxygen here to begin with, but now it's sort of expanded. And so just to come back to the space that I talked about and put Rock Creek in there, if we make the computation for the hypoxia timescale versus residence time, just as we did in the paper, the circles here, if we look at what we had directly observed, it's more like on the timescale of a day or less. So there's actually a little bit of a discrepancy here. And the absolute difference is not really that big compared to this whole scale, but the relative difference is actually pretty big. And this just could be that the initial oxygen concentration just isn't as high as we typically computed it. But there's also the possibility that, that's the wrong direction, that this low oxygen water here sort of set it up to be limited sort of advectively after the experiment. So the last system I want to talk about is this Corsica River estuary. This is on the eastern shore of Maryland. It's also really small and shallow, but unlike having this urban nutrient effect, it's pretty highly agricultural. And this is just that same dissolved oxygen time series that I showed in the first slide, where you can see that that seasonal depletion is there, sort of driven by solubility, but then you have all this high frequency variability just because it's so productive there. Chlorophyll's in exceedance of 100 regularly. And another way to look at this diel-cycling hypoxia is that you can see over the course of about 4 days here that at night the oxygen is going down. During the day it's crawling up to almost 15 milligrams per liter. The sun goes down and it's creeping down to almost hypoxia. So there's just really extreme variability in the system in response to that. And the best predictor of how often these systems are hypoxic, just the hours over the summer, relates to chlorophyll averaged over the summer more than anything. So this is just over a number of different stations in that system where we have this kind of information. Okay. So now if we come back to this timescale plot, here's Rock Creek, we'll leave it there, and the Corsica River sort of falls here. And this is for both approaches. So this is taking the oxygen time series and directly saying how long it took to get hypoxic, and then comparing that to the timescale we'd compute from the respiration rates and the sediment uptake rates. So the point here, I guess, is that these really shallow, really eutrophic systems, they fall in line in this state space here, but they're just at, like a really small time scale. Okay. So in summary, there's this great diversity of coastal systems experiencing hypoxia. Same processes are at play, but there's, a relative importance that varies. The respiration rates that we used in this analysis were just really different for these sites. Even at low rates of oxygen consumption, you can get hypoxia if either the residence time is very long or the source water is oxygen poor. And we've actually sort of talked about that a lot this morning. This ratio of hypoxia timescale to residence time, gamma, it provides a really simple but sort of a consistent quantitative framework to do these kind of cross-system comparisons. In river-dominated systems, hypoxic zone scales with nutrient load. And then in these really small systems, we can have really short-scale hypoxia just because of high nutrients in the chlorophyll that's related. And that's, I guess, what I just said there. So the one thing I didn't talk about is how climate would affect all of these things. And I think Margie's going to talk about that next. But I think if you looked at this talk, you would clearly see that the initial oxygen concentration, which is in the numerator of gamma, should go down with increased temperature. And the respiration rate, which is in the denominator, should go up. So both of those things are really going to work together to make this hypoxia timescale shrink. Thank you for your attention. questions?
I'll start with a question. So I can understand sort of your residence time framework for something like an enclosed bay, like Chesapeake Bay or something like that. But in Namibia, like the Benguela upwelling, I assume that's what you're thinking about. There, it's much more open, and I could also imagine that you could have sort of like water filaments sort of transiently passing through, and then you have water coming in through the core of the Namibia upwelling zone. And so how do you think about a residence time in a much more open system like that, and where you have very different respiration rates, whether you're in the core versus at the edges?
Yeah, well, I think your question kind of points out without saying it that there's, this control volume kind of approach, it probably has only a limited application to these systems where there's clear, really strong 2- and 3-dimensional circulation patterns. And so, I don't know that I have a great response to your question, but I think what I will say is I think this approach is better for sort of enclosed systems, like you said. We only had, one real upwelling system, in the analysis, and I think that's for a reason. So I'd agree that it's kind of limited in those places.
I wondered how you calculated residence time in the two smaller, well, in any of the estuaries, and like how much variability there was in the larger systems. And then also I wondered if you'd thought about things in terms of age instead of times, because like people have made distinctions of the age of water versus the residence time of particularly in estuaries, but also in the ocean. And then also if you, instead of thinking of times, if those were rates, how those three approaches might change your, like, the way you interpreted what you did, or how that new information fit into that state space?
Well, that was 3 questions, but I think the answer to the first one is that we used estimates that were available in the literature for everything, right? And it's fundamentally a mean kind of analysis, and so we're not characterizing that variability in residence time, and we're not even really accounting for the complexity of computing a residence time, right? So I think there is variability around all of this. The other thing that the initial oxygen concentration, that's, I think, one of the more unconstrained things that we're doing in this analysis. And it kind of comes back to your question about source water. And I think putting Namibia and the Gulf of St. Lawrence on there, what that kind of reflects, I think, is the source water issue, is that their source water is just low. So it comes down to that water age, maybe more than it does residence time.
Yeah, Andreas Oschlies again. The question about possible feedbacks or non-linearities in the question. Your concept is pretty linear. You have one timescale for respiration, one for water residence time. But once you have denitrification or nitrogen fixation in the system, you may have feedback loops that suddenly accelerate the respiratory potential a lot, and respiration as well, possibly. Do you see that in any of the data, that you have any deviations from your log-log linear line? Or?
Yeah, so are you asking about nonlinearities in the respiration rates themselves, or in some of the other associated biochemistry?
Yes, in your respiratory timescale, basically. Since that might vary during the season, once you change redox conditions, the timescale might start changing as well.
Yeah, we didn't consider that. I don't know that I have a good answer for you on my feet right now, but let's talk about it. I didn't see that, but again, we're sort of considering kind of a mean condition here, so I don't know that we would see it. It's that simple.
Great. Thanks, Jeremy.